Okay, the first speaker of this session is Pavan Kumar Aluri. Is going to talk about parity-wise alignment of Cmb multiples. Please.
Thank you. Let me start by thanking the organizers for giving this opportunity to speak here. So the topic of my topic is essentially about unusual alignments among even or odd multiples only, as seen in CMB on very large angular scales. So these alignments are separated by among only even multiples and odd multiples. That is essentially the topic. So of course I don't need to flash this. All the audience know the utility of CMB. So one of the foundation assumptions of modern cosmology is that the universe is homogeneous and isotropic. So early on it was a simplifying assumption for making analytical progress, but eventually now starting with WMAP, for example, WMAP, it is the data is sufficiently precise to put this assumption to robust tests, and that's what led to what are called the so-called Cmb anomalies. There were many instances of isotropy violation in terms of power or in terms of directions at low multiples predominantly in Cmb maps. So I'm going to list very few of them which are relevant to my topic. So one of the early ones is the alignment of the quadrupole L equal to 2 and the octupole L equal to 3. They were almost aligned up to a within separation of 5 to 10 degrees depending on the specific cleaning procedure that was used for CMB in the CMB analysis, and likewise there was also this planar. The L equal to 5 mode was found to be highly planar. You can see visually also that it is roughly pointing in this direction. So these arrow marks are just put there just to guide your eye. So the directions were inferred. So with a multipole, you can employ a scheme to essentially associate a vector to it, a direction to it, rather axis to it. So that is done through what is called this angular momentum maximization vector that was proposed by Tegmark et al. And this planarity was also a similar statistic that was a statistic proposed by Tegmark et al. And along with dipole, this quadrupole and octupole all point towards the Virgo cluster. So this is one of the earliest anomalies in CMB that was studied extensively. And then there was this hemispherical power asymmetry, which is essentially that the power spectrum CL of CMB map of CMB is supposed to be rotationally invariant. But however, when you compute the power in different hemispheres, so there is an excess power in one hemisphere compared to the other given by this direction, and this has come to be modeled as sort of a dipole modulation of otherwise isotropic CMB anisotropies. So this direction is given is pointing in this direction, and the amplitude is roughly at the level of 7%, 0.07, and the significance is about 3 sigma. So, and then there is what is called this mirror parity asymmetry, and again this is also a large angular scale multipole. So when you can make a choice of some axis n hat, and with respect to that, when you compute this sum or difference of the CMB pixels in with respect, the pairs that correspond to the mirror symmetry with respect to the chosen direction, then you can define this excess mirror parity or maximum mirror parity or minimum mirror parity, maximum odd parity. So, and it was found that the odd mirror parity is anomalous at the level of 1 to 2%, as given here. The p-values are given here, 1 to 2%, depending on the cleaning procedure that was used, and I will show the directions eventually. But the odd mirror, there is a preference for odd mirror parity in the data compared to the even mirror parity. So the even mirror parity, you can see that it is inconsistent with the expectations, but you can see that the odd mirror parity is at the lower tail. And then there is also this point parity asymmetry, in the sense that if you look at the correlations in the 2-point correlation function of opposite directions, the antipodal correlations, then it can be given simply by the difference of the power in even multipoles and the odd multipoles. So in the standard model, you don't expect that there is a preference for more power in even multipoles or odd multipoles. So if there is any departure from a standard model expectations, then there will be a preference for even or odd power. So indeed, it was found that there is a preference for odd parity, in the sense that when you choose this Lmax, so this 2-point correlation function, as you know, it is given by this sum of 2l plus 1 Cl. PL of cos theta, but for theta equal to pi, you get minus 1 power L. So this power up to some chosen L max, if L max for 22, it achieves a significance of approximately 2 to 3 sigma. So there is more power in odd multipoles compared to even multipoles. So this essentially prompted me to look at to also ask, like, is there any directionality that we can associate with this point parity? We cannot do it similar to the mirror parity in real space. So that is essentially the motivation for doing this work. So there is a power asymmetry between even and odd multipoles, but can you also assign a direction for this even odd multipole asymmetry? So when you just plot all the directions that I discussed so far, this is the L equal to 2, 3 alignment direction, L equal to 2, 3 directions. You have to remember that the statistic is the statistic does not give a direction; it only defines an axis. So just like how you can how they are plotted here, you should also be plotting them here, because it essentially defines an axis. So these are the L equal to 2, 3, but given that the dipole is known, Cmb dipole is known, they are generally plotted in the upper hemisphere. So this is the dipole, Cmb dipole, and then this is the even mirror parity, maximum even mirror parity direction, and this is the maximum odd mirror parity direction, and this is the dipole modulation axis, which is also a parity violating phenomena, in the sense that because it is a dipole modulation, so it is also a parity violating phenomena. So this work is essentially done. This work is done in collaboration with John Ralston at Kansas University and Amanda Weltman at UCT. Our statistic is power tensor, as I alluded to earlier. So there is this well-known statistic, which is the angular momentum maximization, and what you need to do is that you just have to search for this statistic m square mod AL m square sum over L for a given L. For a given L, you have 2L plus 1 m modes. So you just have to compute the statistic and do a search repeatedly of this by rotating the CMB map bringing some arbitrary direction n hat to the z direction, and just compute the statistic. Whichever direction has this maximum returns this statistics as maximum, that is going to be your maximum angular momentum. That is going to be the preferred direction for that multipole. So this is for a specific multipole. So m goes from minus L to plus L. So, but alternately, rather than doing those repeated searches, you can also try to expand this angular momentum maximization vector in this fashion and convert it into an eigenvalue problem. So this Aij is what is called the power tensor that we are going to use, and this is a 3x3 matrix. As you know, these are the angular momentum operators Ji, Jj for a given in spin L representation, and AL vector is essentially the ALM modes. For a given L, there are 2L plus 1, this is a 2L plus 1 by 1 column vector. So what the power tensor does is that a complicated pattern on a sphere is essentially mapped to a ellipsoid. So the eigenvalues of this power tensor will give you the length of this ellipsoid, and the directions and the frame is given by the eigenvectors. So given how much deformed this ellipsoid is, you can essentially define that there is asymmetry in that particular major axis. So that's what we are going to do. So this is formally the definition of power tensor with some normalization factor, because we wanted to, so in the case of isotropy, this Aij as a statistical ensemble, statistical average is going to reduce to CL by 3 delta Ij. So this is going to be diagonal, on the eigenvalues are going to be CL by 3. So that is why this normalization is chosen. And once you have this normalized eigenvalues and the eigenvectors, you can define an axis. You can associate a axis with a multipole as the eigenvector corresponding to the largest eigenvalue. So, and analogously, you can define, okay, in a given realization, you will always get an axis, but what is the significance of that axis? So, which is essentially given by the deformation of this ellipsoid. So, to characterize that, we use what is called the power entropy, which is essentially the usual definition of the entropy definition, pk log pk here, but we are having this normalized eigenvalues. So now that you have an axis, okay, now that you have an axis, you can also compute collective alignments using this outer product called the alignment tensor, and you can also characterize the significance of that alignment using what is called the alignment entropy, similar to this. So let me go to the results. So what we did here is that we chose the multipole range L equal to 2 to 61. So we are analyzing the first 60 multipoles and trying to see cumulatively how much is the alignment among these even multipoles and odd multipoles separately. So the pluses here are showing represent the even multipoles, and the dots here correspond to the odd multipoles. So as you can see, the even multipoles are studied in a cumulative fashion. Likewise, the odd multipoles are also studied in a cumulative fashion. So the lowest bin is 2, 4, 6, and then 3, 5, 7. So this dot here corresponds to the alignment vector corresponding to these 3, 5, and 7 multipoles, and likewise here. So as you keep increasing the bin size, the even multipoles have a tendency to be aligned along the dipole direction, and the odd multipoles span a wider range, but essentially contain all this odd mirror parity axis and the odd parity dipole modulation axis, and the even multipoles cluster towards the kinetic dipole direction. So this kind of brings to us this region that is identified in the WMAP 7-year analysis, that there is this these 4 fingers which correspond to some cold regions. So this is not the same probably region, but essentially it is closer to that. So this broad region that spans here corresponds to that region in some sense. So what is the significance of these alignments? So we find that the odd multiple alignments are highly significant, highly anomalous, whereas the even multiple alignments are not so much anomalous. So this is for the case of a cumulative alignment analysis with increasing L. So we chose the range from 2 to 61 in an increasing fashion by increasing the L max from 7 to 61. So we can do the same exercise in the other way around. So in the chosen multipole range, we go towards the end of this multipole bin and see that the odd multipoles essentially settle down here, settle down near the galactic plane, and this is the 60. Like you remember, the odd mirror parity axis, the dipole modulation axis is essentially closer to this near the galactic plane, and this is the odd mirror parity axis. But however, the even multipoles start slowly drifting from the dipole direction towards the galactic plane. So this is a full sky map as provided by the Planck. So maybe there is this. So maybe this is happening because of the residual contamination in that in the map. So and the significances are given here for the L-min case. So here we see that for the beyond this 28 or so, there is some sort of a clustering. Of course, this is expected because there are a lot of multipoles axes that are settling in the galactic plane. Maybe that is why you are having this huge alignment entropy spiking up, becoming anomalous. But beyond that, you can also, this is a cumulative way of looking at it, but you don't know which alignments are essentially leading to this sort of a anomalous alignment among even multipoles and odd multipoles. Even multipoles, we now realize that they are not anomalous, but only we have to study the odd multipoles. So for that, we define what is called this Hilbert-Schmidt inner product. Like these are the principal eigenvectors. Then they can be converted into an operator like this, projection operator, and you can define what is called a Hilbert-Schmidt inner product. And they have a known PDF which is given by this, and then a cumulative PDF is given by this. Now that we know this analytical PDF of this Hilbert-Schmidt inner products, we can compare them with data. So let me skip to the PDF, the CDF. This is the cumulative distribution function given by the square root x. So this is the analytic value for whatever the values that you get here, whatever values you get from the data, the theoretical value, and then these are the that are seen in the data. So you can see that the multipole range, this red curve corresponds to 26 to 61, which is which we found in the L-min case, and this is the bin that is between 2 to 25 that we found for the L-max case. So they both are very deviant from this expectation, but however, when you compute the whole range, consider the whole range, it is not anomalous. And likewise, it is the same with the even multipoles, they are not anomalous, but only the odd multipole alignments are somehow anomalous. So, and correspondingly, you can compute the Anderson-Darling statistic and also compute the p-values. You find that again in the low multipole region, there is this odd alignments are significant, are anomalous, and even multipoles are not. Even multipoles are not, and these alignments are stable. So what I did, I used essentially the full sky maps. So there might be some residual contamination. So what I did was I cut a part of the sky and in-painted it. So 10% in-painting and 20% in-painting was done here, but up to 10%, this phenomena is retained, so to say. So this is the summary. Of course, I went through that already. So there is the anomalous, the even multipole, there is some clustering, but however, they are not anomalous. But then there is also this, there is anomalous clustering or alignments among even multipole axis, and these actually group according to the parity phenomena that are seen in CMB. For example, the mirror parity or odd parity. So I just make some claims that the L equal to 2, 3 may belong to two different groups that are actually anti-parallel, not parallel, in the sense that, like you saw, there is this clustering of even multipoles here in this direction, and odd multipoles span this direction. So maybe they are anti-parallel, they are not really parallel. And then this L equal to 5 belonging to this odd multipoles might be pointing in downwards. And then probably we have to look for a common origin of the low multipoles in parity properties, whether it is mirror parity or point parity, I am not sure, and I don't know why it is parity in the end, but this is the common origin may lie probably in this. Thank you.
Okay, thank you. Maybe short question for Pavan while the next speaker setup.
Okay, went too fast.
So there was some earlier work that claimed that some of these alignments may be explained by the local ISW.
Yeah, that is true. But that is a theoretical approach. But what I tried to do is, within the data, is there any explanation or a phenomena that binds all these seemingly disparate phenomena? Alignments of L equal to 2 probably, and then dipole modulation axis, and then mirror parity axis, and point parity asymmetry. So these are all disparate at this moment. We don't know an explanation. So I tried to identify from the data, is there any common origin? And then probably the parity properties, we have to look at the parity properties of low multipoles to be able to, probably the origin lies in that. So what you said about this ISW effect is, I'm not sure whether it induces any parity. I don't think it induces any parity-like phenomena. So maybe it is just subtracting something which is leading to that reduced significance of these alignments, of these anomalies. But probably if you if you were convinced about my procedure, then probably you have to look at this parity phenomena and the large angular scale, why it is arising, and probably some theoretical models, or I don't know, maybe systematic.
Okay, thank you.